All right, section 9.6 is power series, and we're going to take a look at taking this idea of series that we've been using and expand our discussion to include cases where the series are a function of the variable x. So we're going to have series that are going to have x in them, as well as the k, which is the index of summation that we've been using. All right, so this is by definition what a power series is. Do you see the x in there? So it's right here. We have a coefficient b sub k, and then and it changes potentially, at least based on what the sequence term is that you're on. But you've got x minus c. C is some constant, just some number. And then this x minus c is raised to a power. So the first time you see, these are just the coefficients, right? B0, B1, B2, B3, and so forth. There's some number out there. But the parts that match is they all have x minus c in them. But the power on them is changing every time. So the first time with b sub 1, we have x minus c to the 1. And then when we have b sub 2, we have x minus c squared. And then b sub 3, we have x minus c cubed. Okay? So that's what's going on with the power series. And in general, what we're going to be looking at when we look at power series is we're going to be looking at what values can x be and allow this thing to actually converge. Okay, we've been working on convergence versus divergence in a lot of different tests so far. But now what we're going to be doing is we're going to be identifying what values for x will we actually see this series, this power series, converge. And there's two pieces of information we generally look for. We look for the interval of convergence, and we look for the radius of convergence. Those are the pieces of information we're going to be looking on. Okay, so what interval of values of x are going to work, and what radius works. So we're giving any of these power series, there's exactly three possibilities of what can happen. One possibility is it doesn't matter what x is. It's going to converge absolutely everywhere. So negative infinity to infinity, and the radius of convergence is what we would sort of by default call infinity. That feels awkward a little bit to me, but that's the way that it's defined whenever you work with this. So the series converges, in essence, everywhere. Option number 2 is the opposite extreme. And it isn't that it converges nowhere, but it will converge exactly when x is equal to c. Now think about that with our series. Why would that work? Why would x equals c force this thing to converge? Yeah, because this right here, this piece of the series, as part of the sequence, would become 0. So you definitely will have one location where this is going to converge. It's precisely when x and c are the same quantity. Okay? But it could be that that's the only place. So the second option here says the series converges only for x equal to c, and then it diverges everywhere else. I think that should say for all other values of x. I think I got a little carried away. And then the radius of convergence would be 0 because it doesn't have any radius, right? It's just at one particular point. It's the second one. However, most of your places are going to fall into number 3. There's going to be some sort of an interval. Okay, so you're going to have some value for the radius that's not 0. So you're going to have some distance away from c on either side. And then it's going to diverge outside of that interval. So sort of your image looks like this. Here is this value c, and you've got some value over here that's r away. And so on this interval, it converges. And over here on the left and on the right, where I put my x's, it diverges. That tells you the interval. It also tells you the radius, right? Because it's going to be whatever that length is on either side of c. The thing that it doesn't tell you, and the part that's actually maybe easy to forget if you're just flat out looking at the details of how this is written, is it doesn't tell you what actually happens at these endpoints in particular, because they're neither included in this notation, because this says less than and greater than, nor are they included in this notation because these are the strict inequality symbols, right, with the open parentheses. So what we have to do when we're in this third case is we actually have to test those particular points one at a time. They aren't difficult to test. We just have to remember to do it. Okay? We're going to do a couple of examples of this. And one of the examples is going to follow this pattern. And the other example is going to follow one of the other two patterns. The other two patterns that happen are pretty easy, and they're very short when you find them. You don't have a lot of work to do to show either of these cases. So these are the ones you'd love to see happen a lot, right? But in reality, this is the one that happens the most frequently. Okay? So we're going to start out with the hardest one. This is the hardest example of the day. I don't usually start out that direction, but we are today. All right, so we've got a sequence. I've got k equals 0 to infinity of k over 2 to the k, x to the k. And it says to determine the radius and interval of convergence. Now, there's a little note that I want you to write down on this. All of these problems that you're going to be using are going to be done with the ratio test. That's helpful information, right? You don't have a whole bunch of tests to use. And the reason they're going to be done with the ratio test is because with the ratio test and you have exponents, they simplify. Right? The ratio test talks about taking the ratio of the k1 term and the k term. Let me say it that way. The k plus 1 term and the k term, and doing a ratio. Well, things simplify very nicely with the ratio test with exponents. And that's what we're going to see happen here. So the start of this is that we're going to use the ratio test. And we need to cite that we've used that. Just like when you were not remembering to cite sometimes that alternating series on the last homework assignment, you need to cite when you're using the ratio test on this, okay? So we are going to be using the ratio test. So you could say use it or you are using it. I don't really care about the verb tense, but you need to cite that it's ratio test that's being employed here. And we're going to talk about taking the limit, and this is the ratio test, as k goes to infinity, of the k plus 1 term. So this is k plus 1. And we'll just put this x on top times x to the k plus 1 over 2 to the k plus 1. And I'll write it properly just in terms of how it's sort of written in the form itself. And then you're dividing by the kth term. So you're dividing by k, x to the k over 2 to the k. Now, you don't have to write it this way, right? I don't have to write a double fraction, complex fraction notation. What could I do instead? Multiply by the reciprocal. So if you don't want to start here by writing this, and I'm going to cut mine and redo it, you can start by doing this as multiplying by the reciprocal. So the reciprocal then would be 2 to the k over k x to the k. And the ratio test has this in absolute values, by the way, so we need to have those there as well. On this one, it doesn't really matter. All these values are positive. Agreed? And that's almost true. It's not quite true because we've got x involved now, but all the other pieces are positive. So we'll come to that information in a minute. All right, so this is really helpful information. Let's take a look at the pieces that simplify. Let's look at the x to the k plus 1 and the x to the k. How will that simplify? I'll get an x on the top. Now, it's worth noting that the k plus 1 on top and the k on bottom, those don't simplify. I'm just going to write them sort of on top of each other as the first piece of here. But the x to the k plus 1 and the x to the k, those do simplify. The other thing is that the 2 to the k plus 1 and the 2 to the k also simplify. How will they simplify?
Playing with it out there?
I don't know. It sounds like they're playing with the sirens out there, doesn't it? How will this simplify?
Oh, you just get 2 on the bottom.
Right, I get a 2 on the bottom. Exactly. Now think about this in terms of limits. X and 2 are not involved in the limiting process of this. They're just going to be x and 2. They aren't changing as k goes to infinity. However, what happens to the k plus 1 over k? What's that limit? It's just 1, right? Yes? I think we've done that plenty enough here to notice that we don't really need to go through and multiply by the 1 over k. If you need to see the multiplying by the 1 over k, do it. If you don't, that's fine. They're not expecting you to actually write that out here. But they are expecting you to recognize that this actually ends up becoming just x over 2. Inside of absolute values, because x still has the possibility of being negative. Now, when in the world, according to the ratio test, will this limit, will this series, let's say it that way, will this series converge? What does the limiting value have to be? Flip to the ratio test if you don't have it out. Go ahead and grab something to take a look. The ratio test tells you when this limit, what this limit needs to be for this series to converge. What does this limit need to be? Less than 1. So this value here at this end, this absolute value of x over 2 has to be less than 1. So our goal is exactly where we are right now. We want to get to the point where we've got an inequality in terms of x and in terms of a constant that we can solve. Now, you have lots of different sort of things you probably remember about solving these. I'm going to write it out in interval notation, or in inequality notation, excuse me. And that inequality notation looks exactly like this. I call them triple inequalities. I've never actually seen that in print anywhere, but that's what I call them. Okay, so in order for this to be less than 1, it means the distance between this and 0 needs to be less than 1. That means it could be clear over to -1 or all the way up to +1. And in general, this is always going to say less than 1 using the ratio test. And you're always going to get this triple inequality that then you're going to solve for x. And in solving this for x, what do you find? Yes, so, and I'm going to write it sort of from left to right. This is -2 is less than x is less than 2. Or we can write this as an interval -2 to 2. This actually tells me the interval and the radius. I've got an interval -2 to 2. This means my radius r equals what? 2. It equals 2. The radius is going to be how far they are apart divided by 2. Right? Think about the radius of a circle. You don't take the two sides of the circle. You start in the middle. So halfway between these is 0, and from 0 out to either end is the value of 2. What it doesn't tell us, however, is whether or not the -2 or the 2 actually work. Are you guys with me? We have to test those two endpoints. Sometimes they will work. Sometimes both will work. Sometimes one will work. And sometimes neither one will work. So we just have to test them. So we're going to test the endpoints. It doesn't matter what order we test them in. So we're going to test x equal to 2 and -2. I'll do -2 first just because it's listed first. So this means that I've got the summation from k equals 0 to infinity. I've got k over 2 to the k. And then my x value is -2 to the k. Okay, everybody good so far? Perfect. All right, so what I want to know then is how I simplify this and then go about testing this particular series, which is something you've seen before, or a variation of something you've seen before, to see if it converges. Okay? So first of all, what do you notice when you look at this? It's alternating, right? This is 2 to the k, this is -2 to the k. Can those simplify in a nicer way? How can they simplify in a nicer way? I'll reword my question. How can they simplify in a nicer way?
-1 to the k.
Yeah, this is just -1 to the k. And it's times the k that's already in the function, right? So it is an alternating series, just like Nathan said to begin with. It's alternating, and now it's actually in the form where we see it look like an alternating series. So how do I decide if an alternating series converges or diverges? What do I do?
What the limit is?
You do the limit of what part, Cameron? Do you remember?
Just the k.
Yeah, you do the limit of the part that's not alternating, right? So in this case, you're right. It's just this k. That's the only part that's not alternating. So we want the limit as k goes to infinity of k, and that is infinity. So by the alternating series test, I'll abbreviate AST if you do, I'm okay with that, but alternating series test, since the limit as k goes to infinity of k does not equal 0, and I'm just going to write out the series diverges. So x equals -2 as an endpoint, it doesn't converge there. Next, we have to test the other endpoint. X equals to 2. So this is the summation from k equals 0 to infinity of k over 2 to the k times 2 to the k. What can you tell me? How does that simplify?
Just get K.
Yeah, you just get plain old k, right? This is the summation from k equals 0 to infinity of k. Now what?
Can you use P series?
I don't think you're going to use p series simply because I don't have a denominator, at least in order to write it in a way that it doesn't work, yeah. Something else.
Can you use the geometry?
It's not geometric because it doesn't have an exponent of k. You guys can tell me, you know, does this series converge or diverge? Even if you don't know the test, you know what it does. It diverges. Just in practical explanation sense, why would it diverge? What's going to happen, Ben? You're trying to talk to me.
It just gets bigger and bigger.
Yeah, the k value just gets bigger and bigger, right? So this sequence that's actually being represented here is 1, 2, 3, 4, 5, so forth. So obviously that's not going to stop adding value to it every time, right? There's a test that says that this is going to diverge. This diverges by the kth, I don't know how it's called, kth series, kth something.
term.
Kth term, is the word used, kth term divergence test. The kth term divergence test says that if the limit isn't 0, which it's not here, right? The limit of this is definitely not 0, that it definitely can't converge. And that's what we're using. Remember, the kth term divergence test says nothing about whether it converges. It can only tell you if it diverges. And that's exactly what it tells us on this. This diverges. So we don't get those values of the endpoints included. This piece that I wrote over here actually is exactly what it wrote, what it is. The interval is -2 to 2. So I'll write it over here. The interval of convergence is -2 to 2, and the radius is 2. Now let's say, just for the sake of argument, that I had found out that -2 actually was convergent. The series converged at -2. What would I do differently in this final writing of my stuff? The answer. I'd use a bracket. So if you found out that either of these particular endpoints worked, instead of using a parenthesis, you'd use a bracket. That's the only difference you would make. Okay, everybody good? Okay, let's see one that works out easier because we don't end up in case 3. All right, here's an example. It says determine the radius and interval of convergence. And we have k factorial, x plus 1 to the k, and we're finding the summation from k equals 0 to infinity. What test are we using? It's not a trick question. The ratio test, because that's what I told you, right, Jordan? I told you all of these are going to use the ratio test. Yes, that's exactly what we're going to use. We're going to use the ratio test. And again, the reason the ratio test works on these is because of this k right here being the exponent. When I take a ratio of these, things divide out nicely, right? Because I'm doing the ratio of the k plus 1 term to the k term. So we're going to take the limit as k goes to infinity of the k plus 1, the first term, so k plus 1.
Right.
Okay. So here's that k plus 1 factorial. I have x plus 1 to the k plus 1. And this is all over k factorial, x plus 1 to the k. All in absolute value, right? Sorry, my absolute values are a little slanty there. Okay. Let's deal with the factorials first. We've seen these happen before back in, I don't know if it's 9.1 or 9.2. And we talked about what happens when we have k plus 1 factorial over k factorial. What's going to happen there? Anybody remember?
K plus 1.
Yeah, you're going to get k plus 1. The k plus 1 factorial is really k plus 1 times k factorial. We talked about this, at least I know several of you talked about it with me when you were doing questions on the board, that remember this just means writing out k plus 1 times k minus 1 times k minus 2. And that's going to be the same thing with the k factorial on bottom. It's going to be k minus 1, k minus 2, and they're all going to match, except for this first one on top has an extra term, k plus 1. So that's the only piece that remains when we start canceling out like terms, is the k plus 1. How about that x plus 1 to the k plus 1 over x plus 1 to the k? What's going to happen there? How's that going to reduce?
You get x plus 1.
On top, right? Did I write that okay, Cameron? All right. Which means I don't really need a denominator, yeah? All I end up having is this part that I just wrote in green left. I don't know about you, but that cleans up quite a bit. Agreed? Now take a look at this. This k plus 1 right here, this is a positive term no matter what k is. So it doesn't really need to be inside of the parentheses per se. Agreed? It wouldn't affect anything. So if you wanted to think about it sort of like pulling it out or something like that, that would be okay on that part of it. But the x plus 1, that part actually could be negative. So we're going to rewrite this one time. Now think with me on this. The x plus 1 part does not have anything to do with the limiting procedure, right? But the k plus 1 does. So what is the limit of the k plus 1 as k goes to infinity? That's infinity. Agreed? So this whole thing has no chance of converging except when? I mean, this whole thing goes to infinity except when? Yeah, except if x equals negative 1. And what happens, Nathan, when x equals negative 1? Yeah, the whole thing would be 0. So one of two things happens here. Either I get infinity, which is most of the time, or I get 0 when x is equal to 1. So most of the time, this limit's infinity, and if the limit's infinity, the ratio test says that this isn't going to converge. Oh, oops, I left my negative off. Thank you. Yes. Most of the time, this limit, this k plus 1, is going to be dominating what's happening. The only time it doesn't is when this x plus 1 is 0, when this whole factor of x plus 1 is 0. And this factor is x plus 1 is going to be 0 exactly when x is equal to negative 1. Which case does that put me in? Two. I'm in the case where this diverges. It's going to diverge for all other values of x. So this series is going to converge exactly when x is equal to negative 1. So here, let's do it this way. I'll put my answer over here in green. This converges when x is equal to negative 1. Remember, it's always going to converge at least at one point. Diverges everywhere else. And so then the radius of convergence is what? 0. There is no distance around x equals negative 1 for which this also converges. So if it converges at only one point, that radius then of convergence is actually 0. Okay, is everybody good with that? Let's think for just a moment how this could be changed to actually put it as a case 1. All right, so case number 1 talked about having the summation from k, I'm sorry, I'm the wrong one. There we go. Talked about having this be an absolutely convergence. And that's going to happen, going to give me a radius of infinity, negative infinity to infinity. It's going to converge everywhere, that kind of idea. Well, the limit comparison test tells me when this converges. And this is going to converge, like we said on number 1, when the absolute value of this ratio is going to be less than 1, right? So if we were able to actually say that the limit of this thing, in this case, k plus 1 over k, had a limit value of 1. But if you take a look at this sequence right here, k factorial times x plus 1 to the k, if the k plus 1 factorial had been in the denominator, then this k plus 1 would have been underneath this, right? I'd have still had all the k plus 1 reducing and everything. I just would have had the k plus 1 in the denominator instead of up in the numerator. guys tracking with me? I've got blank stares, so I'm not sure. Okay, so all I'm doing is suggesting that instead of the k factorial being here, it was underneath the x plus 1. Okay, if I did that, the net effect was that this k plus 1 at the end would be underneath the x plus 1 down here. If I did that, what would the limit be? Again, the x plus 1 doesn't affect the limit. What would the limit be with having a k plus 1 in the denominator? The limit would be 0, right? And if the limit were 0, then this would converge everywhere. Because no matter what whole number x plus 1 ends up being, if the limit ends up being that it's times something that's 0, which is what I would get any value of x working. Right? If x is 7, okay, 7 plus 1 is 8. 8 divided by k plus 1 is still going to go to a limit value of 0. Okay? So, very small change. All I had to do in order to create something that would do the same kind of a weird situation, and it would require just as much work, which is half the work of the last problem, right? Because I don't have to test those endpoints because the endpoints don't actually exist. I don't have endpoints to check. All right, let's take a look at a different one. This has a different set of directions. This says determine the interval of convergence. We were doing that on the last problems, agreed? And then it says, and the function to which the power series converges. Now, we had a question earlier where I was asking you to figure out what kind of a series we had or whatever. And you guys struggled with knowing which test to use. But can you take a look at this? Ignore the fact that it has an x in it for the moment. Just sort of close your eyes to the x. What kind of series is this? And we're going to use a ratio test on the problems, the ones before. We're not actually going to use a ratio test on this one because it actually has a specific form. You know what it is? Nope, we're not going to use the root test, although I see why you might want to. This has an easier form to deal with than that even. Okay, this is a geometric series. Okay, do you guys remember what geometric series looked like? Geometric series was the summation from k equals, and it was defined as k equals 0 to infinity, I believe. But we could use actually k starting in another place. And then it had the pattern that we had some value a times some rate r raised to the power k. It looked like arc. You guys remember that? Do you see that r to the k present in what we're doing? You've got some value that's going to have some radius to it, some r, and it's raised to a value k. In this case, our a value right now is the value 1. There's just not a coefficient in front of that. The reason I bring this up is because this had a closed form way of finding what the summation was. It's the only one we had like that. Every other time we encountered this, we had this sort of issue with the fact that I might be able to say it converges or diverges, but if I can say it converges, I still don't know what value it converges to necessarily. But with a geometric series, you knew how to find the value that it actually converged to. There was a formula. Do you remember it? Do you know it, Hannah? Did you find it? Right. You guys remember that formula? You can identify what A is. In fact, in our problem, you know what A is. What's A? 1. You can identify what R is, and you can identify it in our problem, too. It's everything that's raised to the power. So awkwardly enough, it's the 3x plus 1. Okay? And then you could actually find a value for that if we didn't have x involved. Well, we're going to use this in the same way, and that's what we're going to use this part where at the end where it says a function to which the given power series converges. These are geometric series. Okay? So if I don't have any other piece of information, I just have something raised to a power of k, which is exactly what you're going to have when we talk about this direction set. It's all going to look like this, something raised to a power of k. You've got geometric series. Now, Before I get to what it converges to, let's do the first part. The first part says determine the interval of convergence. So the interval of convergence, as you know, is related to the radius of convergence, right? Okay. What R value do we need for a geometric series to converge? The R in the formula up there, ARK. What does that R value have to be in order for this to converge?
The absolute value of it has to be less than 1.
Right. And I didn't get the absolute values in like you suggested. I was trying to. I don't actually have R written in the problem, which is why I'm putting little quotes around it. I don't have an R here. But you know what R has to be. R has to be the quantity that's raised to the power of K. The geometric series test says this will converge when the R value is less than 1. The absolute value of R is less than 1 anyway. So we need for this to actually have the possibility that the thing that's raised to the power of K, that expression is less than the absolute value of that expression is less than 1. So R in this problem is exactly this piece of information. So this is going to converge when the absolute value of 3x plus 1 is less than 1. That's not quite as clean solving as the first one I did when I did this, but it still happens the same way. First thing I do is make what, again, I called a triple inequality. A negative 1 is less than 3x plus 1 is less than 1. What would I do to solve this? Somebody say it so we can do it. I'm going to subtract the 1, right? So that I leave the 3x in the middle. And then divide by 3. So I end up finding that negative 1/3 is less than x is less than 0. 2/3, sorry, get the right number in there. Negative 2/3 is less than x is less than 0. So my interval of convergence is negative 2/3 to 0. I don't need to test the endpoints because the geometric series test said it had to be strictly less than 1. If it was equal to 1, it wouldn't work. So I don't have to worry about testing the negative 2/3 or the 0 because I'm working with a geometric series, not the limit when we were doing the ratio test. Now, I can answer the other question, which was what does it converge to? So it's supposed to converge to a over 1 minus r, right? So my a value we already said was 1. My r value is 3x plus 1. So if I simplify this, what do I get? 1 over 3x. Yeah, where's the negative? Oh, because the negative 3. That's what it was. Yep. The negative 3 from the negative 3x for this negative. So this power series converges to negative 1 over 3x. So there's two questions that was asked. The interval of convergence, which I did over here. And likewise, if I were asked the radius of convergence, what would the radius of convergence be on this one? I mean, it's not quite as pretty as negative 2 to 2, where it looks very obvious that it's 2. What would the radius of convergence be? 1/3, because the distance between 0 and negative 2/3 is 2/3. Half of that would be 1/3. Okay? And then it converges to, that's this part over here, the function the power series converges to. We used the fact that this was a geometric series, a over 1 minus r, to find that this converged to negative 1 over 3x. Any questions on that? All right.